In this class, we're going to learn about some of the foundations of cryptography. And we're also going to learn how to use cryptography to solve problems in computing, like how to send messages securely, how to manage accounts on websites, and how to do things like perform computation where you can keep your data secret and still get the result of a function that depends on your data and some other data. The name cryptography has two parts. Crypto comes from the Greek root for secret, to hide, and cryptography is all about using secrets. The second part comes from the root meaning writing. This is the same graphy that appears in telegraphy or photography. What we do in this course and what we do in cryptography involves a lot more than just secret writing. It's really everything to do with secrets. So a better name for the course would be cryptology. Cryptography is used so frequently in practice, though, that it makes more sense to use the name cryptography, even though our concern is with the much larger goal of understanding how to use secrets in general. And cryptology is the science of secrets, which is really what this course is all about. So that's enough to answer the first quiz. And the first quiz will check that you understand the definition of cryptology. So the question is, which of these involve cryptology? Check all the answers that do. Opening a door, and I mean a traditional door using a traditional key. Playing a game of poker. Logging into your account at Udacity. Or doing a search using google.com. And I should be a little more specific for this last one. This assumes you're doing the search today and you're already logged into one of your Google accounts. The answer is all of these involve cryptography. And the reason for that is they all involve secrets. Let's go through each in turn. So the first is opening a door with a mechanical key. What's the secret there? Well, let's look at a key. So the secret is actually the shape of the key. Now that I've shown you this key, there's no secret anymore. If you can look at the ridges on the key, well, you know the secret. You can make a copy of the key and open whatever door this opens. Hopefully it's not something very important since I've just shown the key in a public video. And it's actually possible to do this from a fairly large distance. There was a group of students at University of California, San Diego that showed that from taking a picture several hundred feet away, you could learn enough about a key to create a replica that would open the same door. Playing poker certainly involves secrets. It wouldn't be much of a game if everyone could see everyone else's cards. Logging into your Udacity account involves entering an email and password. And I'm not going to actually type my password now because one of the things I hope you'll start to understand from this class is even if you don't see it because of the stars here, the fact that you can hear the audio of my keyboard would give you a pretty big clue about what my password is and the number of characters. And unlike the key that I showed you, this protects something really important, so I'm not going to expose my password. We will talk in one of the future units about how to manage passwords correctly. This involves a lot of encryption. Your password is a secret, but you also want to manage passwords and check them in a way that doesn't require storing those secrets. You don't want to store passwords in a way that could expose them easily, and we'll talk about that more in Unit 2. The final option, doing a search using google.com, is an interesting one. This actually changed about a year ago, whether or not that involves encryption. And if you try it today, you'll note when you enter google.com, what happens is you actually get redirected to https google.com, and you can see the lock in the browser. This means it's using a protocol called TLS to encrypt all the traffic between you and Google. So both the keywords that you're typing are not exposed on the internet, as well as the search results. And we'll talk more about that in a later unit in the class. That involves both asymmetric and symmetric encryption. There's lots of interesting things about the protocol to protect web traffic that we'll talk about later in the class. So the key point is that secrets are all around us, that they're very useful for solving problems. You're using cryptology all the time, every day. The main things we're going to learn in this class, the first two units will focus on symmetric cryptography and its applications. Symmetric cryptography means both parties have the same key. So if we have two people, Alice and Bob, and in cryptography we almost always talk about Alice and Bob. It's not clear why, but they're useful people to talk about, and they apparently have lots of secret messages to send between each other. And they want to send messages. They want to know that they couldn't be intercepted by some eavesdropper listening on the channel. In symmetric cryptography, we assume that they both start knowing the same key, and they can use that same key for both encryption and decryption. We'll see more what that means soon in this unit. What we'll do in units 3 and 4 is introduce asymmetric cryptography, as well as some applications. And asymmetric cryptography is also known as public key cryptography. And the key difference between symmetric and asymmetric cryptography is that the keys used to encrypt and decrypt can be different. So our message gets encrypted. It means there's some function that takes a message and a key, produces some encrypted message, which we call ciphertext. In symmetric cryptography, the decryption uses the same key. In asymmetric cryptography, the decryption uses a different key. And if the keys are different and unrelated, that means you can reveal one of the keys without revealing the other key. And that's the power that asymmetric encryption gives us. And we'll see lots of interesting ways to use that. And in units 5 and 6, we'll look at protocols that use both symmetric and asymmetric cryptography to solve interesting problems. The reason most interesting protocols combine both of these is because asymmetric cryptography tends to be very expensive. You need big keys, you need lots of mathematics to do asymmetric cryptography, lots of computation, whereas symmetric cryptography can be very efficient. So that's why most interesting protocols, like the one we saw for accessing a secure website, involve both symmetric and asymmetric cryptography. We'll get into both the mathematics and the practice of implementing systems using cryptography, but there's one thing I want to really emphasize and make sure that you understand. Implementing your own cryptography is very challenging. It's something that is very easy to do incorrectly. One example of that to keep in mind, and this is an important thing, so we often think about programs as black boxes with inputs and outputs, and our encryption functions will usually take a key and a message and produce some ciphertext. And the implementations we'll show in this class will be functionally correct. They'll produce the correct outputs. They won't be secure. And the reason they won't be secure is things aren't really black boxes when we use them. There's lots of other things that someone could observe about this. They could observe how long it takes. And when you can observe properties of a function other than their functional behavior, other than just their inputs and outputs, that's called a side channel. An example of side channel is timing. So the time it takes to run this function could vary. It could depend on the message or the key. Most of the code that we're going to write in this class will have that property. We're not going to be adding complexity to our code to worry about things like side channels. But in terms of implementing things correctly, that's really important. And there are lots of ways that code could have side channels. It could affect what's in the cache of the processor, and that could be visible in some way. It could actually affect how much power your processor uses, and people have shown ways to break smart cards by measuring the power consumption as they do encryption, and that gives you some insight into what the key is. So this is just an example of the kinds of things that it's very hard to get right in implementing cryptography. These are things that if you were building cryptography for any important use, you'd have to worry about. These are things we're not going to worry about in most of the code that we write in this class. So you shouldn't view these implementations as secure implementations. The only reason to implement your own crypto is for fun and learning. And that's what we hope you'll get from this class by doing it. But if you actually want to use cryptography to protect anything important, well, you should use a library implementation that's been carefully vetted, that's been written in a way to worry about these kinds of issues like timing side channels, and that other people have looked at carefully enough to have some higher level of confidence that it's correct and secure. So I want to make sure everyone was paying careful attention to that last point, and we'll have a quiz. Should you use any code from this course to protect nuclear launch codes? The answers are no. Check the correct answer. So I hope everyone got this quiz correctly. If you didn't, you'll be hearing from our lawyers soon. So the first main topic we'll introduce is symmetric crypto systems. Symmetric means both encryption and decryption are done with the same key. I want to introduce some terminology that we'll use throughout the course. So we can think of encryption as a function, and it takes as input a plain text. This is the unencrypted message. It outputs a ciphertext, and then our goal is to be able to send that ciphertext over an insecure channel. This could be a wireless network. This could be the internet. This could be a courier carrying your message. Any channel where we can't trust the channel to be secure. We hope what comes out of the channel is the same ciphertext we put into it. Then that goes into a decryption function, and what comes out is the message that we sent in. our cast of characters, we often talk about Alice sending the message, Bob receiving it. We also have malicious characters who might be listening in on this channel. One of those is called Eve for eavesdropper, and she has really big ears and can hear the messages sent between Alice and Bob, but she only hears what's sent over the insecure channel. She doesn't have access to the plaintext that's the input to the encryption function, or the plaintext that comes out of the decryption function at the other end. But she can hear the ciphertext that's sent over the insecure channel. To think about this a little more precisely, the plaintext is some message, and it's selected from a set of messages. So M is the set of all possible messages, and M could be finite or infinite. For a given length, M is finite, and we'll often be thinking about fixed length messages, so there's a finite set of them, and M is some message selected from that set. The ciphertext is C, selected from the set of all possible ciphertexts. And the encryption and decryption functions are functions. The encryption function, as shown here, is a function that goes from an element of M to an element of C. The decryption function goes from an element of C, a ciphertext, to an element of M. In order for Bob to receive the same message as the one Alice encrypted, we need this property that the D function is an inverse of the M function. So we need it to be the case for all messages. The result of decrypting the encryption of that message is the same as the message we started with. We'll talk about that a little more later. Before I go on, I want to mention one very important principle in cryptography, which is known as Kirchhoff's principle. And it goes back to a book that Kirchhoff wrote back in 1883. And the way Kirchhoff stated it was this. This was in a book he wrote in 1883 about military cryptography. Faut qu'il n'exige pas le secret et qu'il puisse sans inconvénient tomber entre les mains d'ennemis. And I apologize for my French, but this loosely translates as the cipher must not depend on secrecy of the mechanism. It must not matter if it falls into the hands of the enemy. So the reason for that, and it's important, what he's focusing on is the mechanism here. So if you think about these two functions we need encryption and decryption. Coming up with new functions or new mechanisms, in Kirchhoff's day, these were mostly mechanical devices that you needed as part of the encryption process. Well, that's a lot of work. You don't want to have to keep inventing new encryption and decryption functions and deciding they're secure and distributing them. What you want is some way that even if your encryption and decryption functions are known, your cipher can still be secure. And the way to achieve that is to use a key. So instead of just having the message as input to the encryption function, the other input to the encryption function is a key. And if it's a symmetric crypto system, that same key is the key that is needed in the decryption function as well. If the security relies only on keeping the key secret, well, then we can make our encryption and decryption functions public. We can analyze them. We can put a lot of work into developing good encryption and decryption functions. And then the security depends only on keeping the key secret. If we think our key has been exposed, well, then we just need to come up with a new key, but we can keep using the same functions. If the function turns out to have a weakness in it, well, that's a much more serious problem. Then we need to develop a new encryption function and argue that that new function is secure. So this quiz is to check that you understand Kirchhoff's principle and understand the terms that we've defined. So the question is, which parts of a crypto system must be kept secret? The choices are Alice, the algorithm used for encryption, the algorithm used for decryption, the keys, and the ciphertext. Check all the parts that must be kept secret. The answer is just the keys. This is the point of Kirchhoff's principle, that we don't need to keep the encryption algorithm or the decryption algorithm secret. We want to make those public so they're carefully tested and understood and analyzed by many people. We want to only need to keep the key secret. The point of the encryption system is to allow us to send the ciphertext over an insecure channel. So that's no longer going to be secret. And Alice is just a silly answer. So now that we have the key, we have three main things, right? We have a message in the space of all messages. We have a ciphertext in the space of all ciphertexts. And we have a key in the space of all possible keys. And we want our encryption function. We'll take a message and a key and map that to a ciphertext. And our decryption function we'll take a ciphertext and a key and map that to a message. And to be correct, we need to obtain the same message after decryption. We need to know for all messages and keys, we have the property that decrypting using that key, and I'm going to use the notation where I put the key as a subscript to the decryption function instead of as an input. But that means the same thing as saying there are two inputs to decryption. One is the key, one is the input ciphertext. And the input ciphertext is the result of encrypting using that same key, that message. And we want to know for correctness that that value must always be the message that was input to the encryption function. Correctness, of course, is not enough. We also want security. And our security property, in an ideal sense, would be that the ciphertext reveals nothing at all about the key or the message. We're going to formalize this a little later this unit. For now, let's think about that property informally. And what I'm going to ask you is a quiz to see whether given functions satisfy our correctness property. So now it's time for a quiz to see that you understand the correctness property for a symmetric cipher. Which of the functions below satisfy the correctness property for a symmetric cipher? And we'll assume both the message space, the set of all possible messages, and the key space, the set of all possible keys, are the natural numbers, so the whole number starting from 1. So each choice is a pair of functions, the encryption function and the decryption function. For the first choice, the encryption function adds the message and the key. For this decryption function, we subtract from the ciphertext the key. For the second choice, the encryption function is the identity. The decryption function is the identity on the ciphertext. For the third choice, I'm using the modulo operator. X modulo y is the remainder you get when you divide x by y. And modulo is a very useful operation in cryptography. We'll see that quite a bit later on this unit, as well as in later units. The answer is the first two of these do satisfy the correctness property. The third one does not. And to understand why, well, let's remember what the correctness property is. That's that for any message and any key, we have the property that when we encrypt the message with that key and decrypt it with the same key, we get the message back. And this is what we need for our encryption to be decryptable. We need these functions to be inverses. So for the first choice, the encryption function is m plus k. The decryption function takes that input, which is now called c, and subtracts k from it. Using the properties of arithmetic, well, this is indeed equal to m. For the second choice, the encryption function is the identity. That gives us m back. Certainly this does not provide the security properties we need. We haven't hidden anything about the message. And then the decryption function is also the identity. It takes in m, gives us m back. So this satisfies correctness, certainly does not satisfy security. The third property doesn't satisfy the correctness property. And the easy way to see that is to observe that the output of this is a smaller set than the number of messages. So there, for some choices of message and key, this maps to the same value. And an example of that would be if we choose k equals 2, if m equals 4, then the encryption of that message is equal to 0, because the remainder of dividing 4 by 2 is 0. But if we also choose the message 6, well, then the encryption with that same key of 6 is 0. Since two messages map to the same ciphertext, there's no way they could decrypt correctly. They can't both decrypt to different values because decryption is just a function. It takes that input. It's going to produce the same output in both cases. In this case, it's going to produce 0. It's not going to produce the message we need. So this is neither secure nor correct. But once it's not correct, we know it's not useful. The first one, as it is not secure, but it's actually pretty close to being secure. And if we combine the first one with a modulo operator and we never reuse keys, we'll end up with something that's perfectly secure. And that's what I'm going to talk about next. I'll introduce the first cipher that we'll talk about. And it's actually a cipher that is perfectly secure. So I'm going to introduce a cipher called the one-time pad. And this is actually a perfect cipher. And we'll define more precisely what that means. But it's a cipher that reveals no information at all about the key or the message. And it's actually the only one. And you might be wondering, well, if we're starting right at the beginning of the class with a perfect cipher, what's there left to do?
It's perfect, but it's very impractical. And the reason it's very impractical is because it requires huge keys. So to understand the one-time pad, the first thing we need to understand is the XOR function, which is a name for the exclusive OR. And it's often written as a plus with a circle around it. The truth table for XOR is this. The value of A XOR B is true if one of A or B, but only one of them is true. So that's why we end up with this truth table. XOR has lots of useful properties that make it the favorite function of every cryptographer. And I'll see if you can figure out one of these on your own. So the question is, for any values x and y, what is the value of x, XOR y, XOR x? So here are your choices: 0, x, y, or it depends on x. So the answer is it's always y. And this is why this is such a useful function in cryptography. If we XOR in the value of x twice, they cancel out. So the general property for any value x, x XOR x is equal to 0. We can see that from the truth table, right? The value of x could either be 0, and 0 XOR 0 is 0, or 1, and the value of 1 XOR 1 is 0. And that means that XOR x is always 0. XOR is also associative and commutative. So that means if we have x XOR y XOR x, that's equivalent to x XOR x XOR y, which is also equivalent to y. And I've written this using x's and y's. If we change the names of our letters to M and C, it becomes really clear why this is so useful in cryptography. If we call x the key, then we have the key XOR the message. That's going to be the ciphertext. And then the ciphertext XOR the key again gives us back the message. And what I've described is exactly the one-time pad. The key aspect is why it's called one time is that we can only use the key once. So if we do this one bit at a time, we need a new key for each bit. If we think of doing it for a longer message, well, then we need a key long enough that we're XORing each bit with one bit of the key. So let's define that a little more precisely. So we're going to find our set of messages is strings of zeros and ones, so we'll use bits, and of some fixed length. So n is a number that gives us the maximum length of a message. Our message is selected from all binary strings of length n. Our key is also selected from the set of all binary strings of length n. And then to do encryption, our encryption function, we're going to think of the message as being this sequence of bits, and the key is also a sequence of bits. The result of our encryption is the ciphertext, which is a sequence of bits, also length n, where the value of each ciphertext bit is equal to the XOR of the corresponding message bit and the corresponding key bit. So let's try an example. And for this example, I'm going to give you the ciphertext and the key and the message. So suppose our message is the string CS, but our message space is in bits. Well, the first thing we need to do is to convert those strings to bits. And we can do that in Python by using ORD that takes a one-character string and turns it into a decimal number. And then we need to convert that decimal number into bits, into a binary number. And we need to do this for each character in the string. We're going to convert it to a character, convert that to bits. And I'll show you the code for doing that. We'll leave the more interesting code for you to write. Here, we're converting to bits. This is a fairly straightforward, but not the shortest way to do this. We're going to make an array of bits as our result. For any decimal number, if it's divisible by 2, we want to have a 0 at the beginning of our result. If it's not divisible by 2, that's going to be a 1. And then we divide the number by 2 as we go forward. So that's going to fill up all the places. We want our bits to be particular lengths, so we have a padding. And for all the characters, we'll use 7 bits. So we're going to pad the result with leading zeros until we get to that size. We could see this. So if we do ORD, we see that the number corresponding to the letter C is 67. If we convert that to bits, and we'll use 7 as our padding, that gives us enough for 128 different values, which is enough for the ASCII character values that we get back from ORD. We can see those bits as a list, and we can see that a little more easily as a string using the display bits procedure that just turns that into a string. So now we want to convert more than one character. to do that, we have a string to bits procedure that goes through all the characters in the string, converting each one to bits using convert to bits, and concatenating those all together to the result. So now we can do string to bits for our 2-letter string, and now we get 14 bits as a result. So if that's our message, then the value of m is what we got there. So this is our message. They're 14 bits, and it's 14. That means to encrypt this using a one-time pad, we need a key that also has 14 bits. So let's pick our key. And we're just going to make up a random key now. Actually, finding random values is very important in cryptography, and we'll talk about that in a later unit. But for now, let's just make one up. So suppose this is our key. Then the ciphertext is just the result of XORing each message bit with the corresponding key bit. So that's our ciphertext. So the question is, as an interceptor, you saw just this ciphertext. You don't know anything about the message or the key, and you're going to guess possible key values to try to figure out what the message is. And what key value would you guess that would mislead you to think that the message was actually BS instead of CS? So the key point to notice here, and this is why the one-time pad provides perfect secrecy, is that for any given ciphertext, we can produce any message we want by picking different keys. That means that if we just have the ciphertext, we haven't learned anything at all about the message. The way to produce the message BS from this ciphertext, well, we just need to change the first letter to be one below where C was. So that means we want to change this bit to be a 0 instead of a 1 in the output. That means we need to flip one bit in the key. So we'll need to change this key bit to be a 1 instead of a 0. Everything else will be the same. This will change the output letter by 1. So if we guess this key instead of the correct key, we get what looks like a fairly reasonable message out, but it would be one off from the one that was there. And in fact, we could get any possible message we want by guessing different keys. So this is what's called a one-time pad. And that notion of a one-time pad goes back until at least 1882. It was discovered quite recently that it was known about this early. There were one-time pads used in World War I and used in many other contexts since then. The notion of the one-time pad being known this early was only discovered last year by Stephen Bellavin. What made a one-time pad really interesting was the analysis that Claude Shannon did. Claude Shannon was the father of information theory. He did some of the first theoretical work in cryptography. During World War II, he studied communication, and he also studied theory of secret systems. And he wrote this paper, which was the first paper that really understood in a theoretical way what it means for a cipher to be good. And this paper was written during World War II. It was classified and released in 1949. So what we're going to look at next is how you formally reason about a cipher being secure and why the one-time pad has all the security properties that make it a perfect cipher. So we saw earlier how we could prove correctness, and correctness is easy to show. Proving security is really hard. This property of the one-time pad that we can change the key and that leads to a different message is the reason why it is secure. But first I want to talk about how to prove security in general, and then we'll come back to the problem of how do we prove that the one-time pad is actually a perfect cipher. So how can we argue that a cipher is secure? And this is a really hard problem. I'm going to start with a quiz, and it will definitely require some guesswork, but see if you can think it through before I explain the answer. I'm going to give you 5 possible ways someone might argue that a cipher is secure. So for this quiz, your goal is to order the arguments below by how effective they are in convincing someone that a cipher is secure. Use 1 to indicate the best argument, and 4 to indicate the worst argument. The choices are many very smart people were highly motivated to break the cipher, but were not able to. That means it must be secure. The second choice, there are 834 quadrillion possible keys, so it must be secure. The third choice, here's the mathematical proof that's been accepted by experts that shows the cipher is secure. The fourth choice, here's a strong argument why breaking the cipher is at least as hard as some problem we already believe is hard. This is a bit of an unfair question, since we haven't talked about this yet, but I think it's useful for you to think about it on your own before I talk about it. So see if you can figure out which of these arguments are most effective. So here's what I think the best answer is. The best possibility is that we do have a mathematical proof that follows standard rules of deduction that shows that the cipher is secure. And there are very few ciphers that we can actually get that for. One actually is the one-time pad, and we'll see that later this unit, how to prove in a mathematical sense that it has a very strong security property. The next best one is the last one, which is to show in a formal way why this cipher is at least as hard as some other problem. And we'll talk about reduction proofs more later in this course. The basic premise here is that there's some other problem that we have good reasons to believe is already hard. And then we're going to show that if we could break the cipher, we could solve that other problem that we already have good reasons to believe is hard. The next best is this one, that many smart, highly motivated people tried to break it but couldn't. This is often the best we can do. And for the best symmetric ciphers that are in use today, this is really the reason that they're argued secure. There may be formal arguments that show why they resist particular attacks, and that's part of smart people trying to break ciphers, is knowing all the known best case attacks and trying them against the cipher and seeing that the cipher resists them. But ultimately, the best we can do is show that, well, we think it's secure because it has these properties and lots of smart people weren't able to break it. But that's not a very satisfying way to know it's secure. We'd certainly much rather have the strong mathematical proof. The worst possible argument here is the key space argument. And this one is often made incorrectly. The number of keys gives you an upper bound on the difficulty to break the cipher, because at worst, the attacker could try all the keys. That's not true for the one-time pad, as we saw. Trying keys gives you perfectly sensible messages that you'll eventually see all possible messages, so you can't know which key is correct. But for ciphers where the key space is smaller than the message space, you could try keys and have a good likelihood, if the key leads to a sensible message, that that's the right message. So this gives you an upper bound on how hard it is to break a cipher. It doesn't give you a lower bound. The fact that you have a large number of possible keys doesn't mean the cipher is secure. We can always add to the key space without increasing the difficulty in breaking a cipher. So we'll see many ciphers with very large key spaces that are completely insecure. So our best possible argument is to have a mathematical proof. And that's what Claude Shannon was able to do for the one-time pad. And it's really a fairly unusual case where we can get a mathematical proof that's that strong. Before getting onto the proof that the one-time pad is secure, I want to do a brief review of probability. If you feel very confident that you understand probability well, it's fine to skip this section. But I think for many students it will be helpful to review probability, and for some this will be new. It's not necessary to have a lot of background in probability entering this class, but we will certainly be using it in cryptography. So to talk about probability, we need to think of sets of outcomes. We'll use omega to represent the set of all possible outcomes. This is sometimes known as a probability space. And for a simple example, if we think about flipping a coin, omega is the set of the outcomes we could get. We could get it to land heads, and we'll call that H, or we could get it to land tails, and we'll call that T. If our probability space has a uniform distribution, that means each outcome has equal probability. And we can write that as a probability using P as our probability function. So P is a function that takes as its input some outcome, and it maps that to a real number between 0 and 1. 0 would mean that event never happens. 1 would mean that event always happens. So if we assume a fair coin with a uniform distribution, well, then the probability that we get heads is equal to 1/2. And the probability that we get tails is also equal to 1/2. So that's how we think of mathematical coins. And we hope to have mathematical coins to use in our crypto systems. Real coins aren't so perfect. So let's assume instead that there are 3 possible outcomes. Now our probability space will be heads, tails, and edge. The edge outcome does not happen frequently. And we'll make the probability distribution, so the probability of heads is 0.49999. The probability of tails, we'll assume our coin is still fair, that the probability of tails is equal to the probability of heads, which is 4 followed by 4 nines. Is that enough to determine what is the probability of edge, the outcome E? So I've given you 2 of the probabilities. Can you determine what is the probability of the third possible outcome, which is landing on the edge, denoted by E? The answer is 0.00002. And the reason for that is the sum of all the probabilities of all the events in the probability space must be 1. We're certain that we get one of these events every time we draw from the probability space. And I'm not going to try flipping the coin enough times to see if I can actually make it land on its edge, the actual probability of landing on the edge is probably much lower than that. The next term I want to define is an event. You might think of landing on the edge or landing on tails being an event. We can define an event a bit more broadly, that it's a subset of outcomes from the distribution. So an example of an event would be landing on heads, and landing on heads as an event is just the set of the outcome H. We could define the event valid for a valid coin toss, and that's the set of the outcomes H and T. The probability of an event is just the sum of the probabilities of all of the outcomes in that subset. So the probability of an event A is the sum over all the outcomes in A of the probability of that outcome. So that should be enough to figure out what is the probability of a valid toss. I'll remind you that we defined probability of heads as 0.49999 and the probability of tails as 0.499999. So what's the probability of a valid coin toss? So the answer is 0.99998. And there are two ways to solve this. One is to sum these two. Not too hard to do. The other way to solve it is to use the complementary event property, which makes the math a little easier in this case. And that property is that we know the sum of all possible events has to be 1. So instead of computing p-valid by adding the probabilities of heads and tails, we can compute it by subtracting from 1 the probability of the events not invalid, which is the probability of E, which is 0.000002. So that would get us the same answer. The property that we're using to do this is the complementary event property. What that states is that for any event A, the probability of that event and the probability of the complement of that event, that is, of that event not happening, is equal to 1. And what the not A here means is the elements in the universe minus the elements in A. So this is set subtraction. We can think of that like this. So this is our universe. If we have some event A, all outcomes that are not part of A must be the complement of A. And that's what you get by removing A from the probability set. The next concept I want to talk about is conditional probability. And this is the one we're going to need to use to prove that the one-time pad is perfectly secure. So here's our definition of conditional probability. If we have two events, we'll call them A and B, and they're in the same probability space, the conditional probability of B, given that A occurred, is written like this. So it's the probability of B given A. So we use the bar to indicate conditional probability, and it's defined by this formula. So it's the probability of A intersected with B divided by the probability of A. To get an intuition for that, let's look at these sets. So here's our universe omega. That's all events. And our question is, given that we know A occurred, what's the probability of A? So the fact that A occurred means the rest of our probability set doesn't matter. We're only considering the outcomes where A occurred. So that's this set for A. We want to know what was the probability that B occurred. So that's the elements in this intersection. So those are the times when B did occur, divided by the size of the set A, which is the probability of A. So that's the intuition behind this formula. Let's see if it makes sense for our example as well. So the question is, given that we have a valid coin toss, what's the probability that it's heads? And I'll remind you the model we had said the probability of heads is 0.4999 with 4 nines. The probability of tails is 0.49999. The probability of edge is 1 minus the sum of those, which is 0.00002. And we define valid as the outcomes where it lands on heads or tails, not on the edge. Given that you know a coin toss is valid, what's the probability that the outcome is heads? And we can compute this using the formula for a conditional probability. In this case, what A is the probability that the coin toss is valid. A is valid, and we know that the probability of A is equal to 0.99998. What B is the probability that it's heads, and so the probability of B is the probability of H, which is 0.49999. And now we just have to plug these into the formula. But what we need to use the formula is the probability of A intersect B. And what A is, the probability of A intersect B, well, what A is valid, the set of heads and tails. What B is heads. So if we intersect heads and tails with heads, well, we get tails. And we know the probability of tails is 0.4999999. So that means, using the formula, we have the probability of tails, which is 0.4999, which is the probability of A intersect B. And we're dividing that by the probability of A, which is valid event, which is 0.999998, and we get 0.5. And I should note that this is not the case for real coin tosses. There's no physical coin ever manufactured that has exactly equal chances of landing on both sides. And in fact, with real coin tosses, at least with American currency, there's a much higher percentage, much higher meaning close to 51% rather than 50, that the coin lands on the same side that it started on. When we talk about mathematical coin tosses, we're going to assume that there's no edge case and that it's equally likely that we have a uniform distribution and there are only two outcomes. When we talk about mathematical coin tosses, we're going to assume that we have a uniform distribution and there are only two outcomes. So now we're ready to define what a perfect cipher is and to see why the one-time pad satisfies this property. So the notion that we want a perfect cipher to mean is that if an attacker intercepts a message, they receive the ciphertext, that provides them with no additional information at all about what the plain text was. So we have a message, it's being encrypted with a key, the attacker is intercepting that ciphertext as it's sent over this insecure channel. What we want to know is that an attacker who sees just the ciphertext learns nothing about the message. So if you followed the definition of conditional probability, you should be able to decide how to define that formally. So we'll make that a quiz. So the question is, which of these is the property that we want in order for a cipher to be perfect? That is, to have this property that the ciphertext reveals no information about the plain text. So I'm going to introduce some notation. So our message is selected from the set of all possible messages. We have some other message we'll call M star, also selected from M. We don't know if M is equal to M star. Both of these we could think of being drawn from the set of messages. And we have some key drawn from the set of possible keys. So for this quiz, your goal is to understand how we can formally define what a perfect cipher is. And this is the scenario. We have an attacker who's heard a ciphertext. We want to know that by hearing just the ciphertext, the attacker has learned nothing new about the message. So we've introduced some notation here. We have a set of possible messages, the uppercase M, and we can select lowercase messages M star. Those are both messages selected from M. The attacker's goal would be to tell, is the intercepted ciphertext the same as message M star? That's the attacker's guess. And we have encryption using some key selected from the set of all possible keys. We don't know what the key is. So here are the possible choices. The answer is the second one. Here we're using conditional probability. So the event that we saw was the ciphertext. So that's the encryption of M. What we want to know is whether the message is equal to M star. Both of those are selected, drawn from the set of possible messages. And in order for the attacker to know nothing, well, that's the same as the probability that the message is M star without knowing the ciphertext. The first answer would be correct if, a priori, the attacker knew nothing about the messages. All the attacker knows is each message is equally likely. In that case, the probability that the message is M star would be 1 over the number of possible messages, not depending on the ciphertext. The problem is the attacker might know something more. They might know that some messages are more likely than others. In most realistic scenarios, this is the case. The attacker knows that, well, the message is likely to be a valid sentence in English. Very few possible bit sequences correspond to that. So all messages are not equally likely. So that's why choice 1 is not the definition we want. We want choice 2, where whatever the attacker already knew about the probability that the message is M star is not affected in any way by seeing the ciphertext. So that's our definition of a perfect cipher. Now the question is, can we prove that the one-time pad has this property? So our goal is to show that a one-time pad is a perfect cipher. And now that we have the definition of a perfect cipher, we should be able to argue that formally. So this was our definition. Since our definition uses a conditional probability, We should also remember the definition of conditional probability, which is the probability of some event A conditioned on event B happening is equal to the probability of A intersect B divided by the probability of B. So to show that the one-time pad is a perfect cipher, we just need to calculate this, where A will be this event and B will be this event. So we need to know the probability of B, which is the probability that some message with some key encrypts to C. So let's compute that first. Then we'll need to compute the probability of A intersect B. So we'll have a little quiz. So given any message and any ciphertext C, and we're using a one-time pad, how many different keys are there that encrypt that message to that ciphertext? The answer is there's always exactly one. For any message ciphertext pair, there's one key that maps that message to that ciphertext. We can see that thinking about the nature of the one-time pad. Suppose we just have 1-bit messages. We have messages 0 and 1. Well, then the key 0 will map 0 to 0. The key 1 will map 1 to 0. And the key 0 will map 1 to 1. But this works for any length message and any length key. Note that the length of the key and the length of the message scale the same way. So if we had 2-bit messages, there would be 4 different keys that would map each message to each different ciphertext. If we had 2-bit messages, there would also be one key that maps each message to each different ciphertext. For example, the key that maps 01 to 10 would be the key 11. So that means we can compute this probability, summing over all the messages, summing over all the keys, where we've got the probability that that key encrypts that message to the given ciphertext. And we need to divide this by the space, which is the size of the messages times the size of the keys. So now what's the value of this summation? So we know for a given message, there's exactly one key that maps it to that ciphertext. So this is 1, and we're summing over all the messages, summing the value of 1. So that means we're going to get the number of messages divided by the number of messages times the number of keys. So that's equal to 1 over the number of keys. So that's the probability of event B, which is the probability that some message encrypts to some key. And notice this is computed over all the messages. So that's over the distribution. But what we need to do now is consider this particular message M star. So we want to compute the probability of the intersection of those events, that the selected message is M star and the message encrypts to C. So I'm going to make that a quiz, see if you can figure out what that is yourself. So here are your choices. See if you can figure out what the probability of M equals M star intersected with the encryption of M equals C. The answer is this one, that it's the probability that the message is M star divided by the number of keys. To see why, let's think about our probability space. So we have all the possible messages being ordered. So we have message 0, message 1, all the possible messages. And there's some message that we've selected that's message M star. We don't want to assume that the messages are uniformly distributed. So the probability that the message is M star is not necessarily 1 divided by the number of messages. If the messages were uniformly distributed, then this answer would also be correct. But they're not. We don't want to assume that. Maybe the attacker has some prior knowledge about the distribution of messages. And that's normally the case. Even if we don't know anything about the particular messages, well, maybe we know it's a message in English, and most random strings of text are not messages in English. The other dimension in our probability space is the choice of the key, and there are k possible keys. So what we want to know is what is the intersection of these two events. So the M star event is this line in our probability space. Each one of these keys maps exactly one message to C. We saw that before, that there's one key that maps each message to C. So we can think of that as being a diagonal line through our probability space. This is the line where the encryption of Ki and Mi is equal to C. Depending on what C is, it might not be a diagonal line. But we can think of it that way, that there's one key that maps each message to each ciphertext. So that means there's exactly one point here where those two intersect. If the distributions were normal, well, that would indeed be the correct answer, that it's 1 point and our space is size of M times size of K. But the distribution isn't normal. We don't want to make any assumptions about the distribution of M. For the keys, we do want to assume that the distribution is normal, that each key is equally likely. the keys are chosen perfectly at random. So we have the probability of picking M star, and we're multiplying that by the probability of picking this intersecting key, and we'll call that K star. But because the keys are uniformly distributed, we know that this probability is 1 over K, 1 over the size of K. We don't know that about the messages, so we leave that probability as it is. So that's why this is the answer to the probability that the message at M star intersected with the encryption of the message is C. So now let's go back to our definition. So we showed earlier that this was 1 over K, 1 over the size of K. Now we've shown that the probability of M equals M star is equal to the probability the message is M star divided by K. So we've shown these two things. Now we just need to plug them into our conditional probability formula. We're going to have this on top, and we're going to divide that by the probability of B, which is 1 over K. The over K's will cancel out, leaving us with the probability that the message is equal to M star. And that's exactly our definition of a perfect cipher. So we can conclude that the one-time pad is a perfect cipher. It exactly satisfies the definition of a perfect cipher, where the ciphertext reveals nothing at all about the key. So you might think the class should be over. We've achieved our goal of perfect secrecy using a cipher that was invented over 100 years ago and is actually provably perfectly secret. So we're not quite done yet. There's some pretty serious problems with the one-time pad. One problem is that it's malleable. So what malleable means is if Alice sends her ciphertext to Bob and our evil interceptor, this time it's not just an eavesdropper, it's an eavesdropper with a hammer. If our interceptor has control over the network, and instead of just being an eavesdropper, can be an active attacker. And an active attacker means they can actually change messages on the network. So the message that arrives at Bob is not C, it's C prime. Because it's a perfect cipher, the attacker can't learn anything new about the message from C, but she could modify it. And maybe she had a pretty good guess about maybe there was a number in the message somewhere or something that she wanted to change. Well, she could flip the bits at that part of the message, change the ciphertext that Bob receives to C. It would decrypt, and with the one-time pad, encryption and decryption are the same function. The decryption of C prime would be M prime, and the attacker can actually control the difference between M and M prime, because the way the one-time pad works is just XOR, so the attacker could decide whatever difference she wants to introduce in the message. This is a dangerous property for a cipher to have. Another big problem with the one-time pad is that it's very impractical. And the real reason that it's impractical is because the keys have to be as long as the messages, and we can never reuse the key. So this is this property that the number of possible keys is equal to the number of possible messages. So maybe what we should try to do is to find a more practical, perfect cipher. Unfortunately, Claude Shannon proved that that's not possible. So that's what we're going to look at next, is why this property that the key space has to be at least as big as the message space is a requirement for a cipher being perfect. And what the theorem essentially says is that if a cipher is perfect, it must have this property. It must be impractical in the sense that the number of possible keys must be at least as big as the number of possible messages. We saw for the one-time pad that they were equal. We can always remove possible messages from the message set, so there's no problem with adding more keys. The problem is we need to have at least as many keys as messages. So let's prove this property, and we're going to prove it by contradiction. So we're going to start by assuming that we do have a perfect cipher that does not satisfy this property. So suppose we do have some perfect cipher, we'll call it E, where the number of possible messages is greater than the number of possible keys. There's some ciphertext, we'll call it C0, it's element of the set of possible ciphertexts. And let's assume that that ciphertext is possible. We know that there must be such a ciphertext, that there's some key that encrypts some message to C0. So the probability that a message and key get encrypted to this ciphertext is greater than 0. So we know that such a ciphertext must exist. Now we have our ciphertext C0. Let's try decrypting that. So we'll decrypt it with all keys in the key space. So we haven't mentioned what the decryption function is. For the one-time pad, it's exactly the same as the encryption function. For this, we don't want to assume this. It could be any function. So we'll assume there's some function D That's our encryption function. Now, since our cipher is correct, right, in order to be perfect, it has to both be correct and perfectly secure. That means the decryption function must have the property that if we decrypt a message encrypted with the same key, we always get the same message out. So we don't need to know anything else about the decryption function than that. And we shouldn't assume anything, because all we're trying to do is show that there is no possible choice for E that is both a correct encryption function and a perfect cipher. So now what happens when we decrypt C0 with all possible keys? Well, we're going to look at the set of messages that we can produce. So we'll call M0 the set of messages that we get by unioning over all possible keys the result of decrypting this ciphertext C0. So this models what an attacker would do. They've intercepted some ciphertext. They're trying all possible keys. This is what a brute force attacker would do. And looking at all the possible messages that can be produced. So now I want you to think about which of these statements are true. Check all the statements that must be true. So this is a fairly tricky question. The first one is actually not true. The reason it's not true is there's no guarantee that the same ciphertext with different keys doesn't decrypt to the same message. So we know that the size of M0 is no bigger than the size of K, because we constructed by unioning the decryption, which produces just one result over all possible keys. We know that it's no bigger than the number of possible keys. We don't know that it's actually equal to that. That would require another assumption about the decryption function. The other two properties we do know are correct. So we know that M0 has fewer elements than M, and this is the case because of this assumption that we said that the space of possible messages is greater than the space of possible keys. So if that's the case, combined with the size of M0 being less than or equal to K, well, then we know that the size of M0 must be less than the size of M. The third property is also true, and this is the key property that should give us the insight why it can't be a perfect cipher, is that there exists some message in M that can't be in M0, and that follows directly from this property. If one set is bigger than the other set, there must be some element in the bigger set that's not in the smaller one. So how do we go from there to prove that it's not a perfect cipher? Well, let's remember our definition of a perfect cipher, and that was that the probability that the message is some particular message, given the ciphertext, without knowing anything other than that ciphertext, is equal to the probability that M star was the message beforehand. That probability hasn't changed. In this case, well, if we have intercepted C0, this was our ciphertext for the example, well, because of this property, we know that the probability that the message is M star is actually 0, because that's not in the set of possible decryptions of C0 over all possible keys. But we said that M star was a message in M that initially had some non-zero probability, which is not the case that these two are equal, because this was greater than 0. So we've contradicted the requirement for a perfect cipher. The only assumption that went into this was this one. We assumed that there existed a perfect cipher where the number of messages is greater than the number of keys. And we've reached a contradiction. So this proves that there exists no perfect ciphers where the number of messages is greater than the number of keys. So this is bad news. Every cipher that's practical must be imperfect. So this means that given some ciphertext that an attacker intercepts, even if the attacker knows nothing about the key, they can eliminate some of the possible messages. So this means when people attempt to use ciphers similar to a one-time pad in practice, they tend to actually not work very well. And the reason for this is that they reuse keys because the number of messages they want to encrypt is greater than the number of keys they have. Next, we'll look at an interesting historical example of this. So I want to show you an example of the kinds of things that go wrong when people attempt to use one-time pads in practice. And this is a story that is very important to the history of computing, as well as the history of the world. And it's how the Allies at Bletchley Park were able to break the Lorenz cipher, which was a cipher used by the Nazis to communicate between the capitals of the cities of Europe. This story goes back at least to the 1919 patent that Gilbert Vernam, who was an engineer working at Bell Labs, got on a one-time pad system. It shouldn't really be called a one-time pad. It was a reuse pad system. And the idea behind this is somewhat clear from the patent. especially if we rotate it so we can see it more clearly. So one thing you can see is that there are 5 wires going into it. And this is the output from reading a tape that encodes the message. The key was also on a paper tape. And the encoding used just 5 bits. So this was the Baudot code. With 5 bits, we can encode 32 different symbols. So that's enough for the alphabet and a few punctuation marks. And you can see the letters were encoded. There's the strip down the middle that was used to align the tape. And then there are 5 bits to encode each letter. Managing paper tapes like this was difficult, and the keys needed to be distributed on paper tapes. If the keys were constructed in a perfectly random way, and you had enough key that you never need to reuse it, well, this would actually be a perfect cipher. This would be a perfectly good one-time pad. Problem is, distributing large paper tapes is pretty difficult, especially if you're trying to do this in wartime. So the machine that was built based around the same idea as the Lorenz cipher machine, where instead of having a paper tape with the key, you had a machine that would attempt to produce a good sequence of key bits. And of course, it's impossible for a machine to produce a perfectly random sequence. The structure of the machine determines properties of the sequence that's produced. So the machine would generate a key sequence based on its configuration. And that configuration is the initial settings of all the rotors and other parameters that we'll talk about soon. If there are 2 machines that start in the same configuration, say one in Berlin and one in Paris, well, then they produce the same key. Their encryption is just the message XORed with the key. That produces the ciphertext. That's sent over radio wireless, received at the other end, which puts it into a machine starting with the same configuration. So that means that ciphertext XORed with the key generated by this machine, starting from the same configuration, will decrypt to receive the message. The machine was designed to produce a large number of possible sequences. There are a lot of complex operations, which we'll talk about a little next. But the key would not repeat for 10 to the 19 letters. So given that this number was larger than the amount of text written by humans, at least at the time, this led the Nazis using it to believe that it provided the highest security they needed. They also were confident that because these machines operated in capitals, they weren't like the Enigma machines, which operated in the field, that they never lost one of these machines, that the Allies never actually had access to the actual machine to try to figure out how it worked. So these links started to be used in May 1941. In August 1941, the Allies had a big break. So an operator was sending a message using a Lorenz cipher, starting with the initial configuration. And these configurations came from codebooks. The recipients at the other end needed to know what the configuration for that day was. But these could be distributed securely and were much smaller than needing to distribute the whole key sequence. Once you had the starting configuration, you could transmit an arbitrarily large message if this assumption that the key was completely unpredictable was true. In this case, the operator sent the message. The receiver did not receive it. So the receiver said, garbled transmission, please resend. And so the annoyed operator had to send the message again over the insecure channel, and this time it was received okay. If this is exactly what happened, it would have been fine. These would be exactly the same. We restarted the machine in the same configuration. But what happened was a little different. The operator got a little lazy the second time. The operator was annoyed having to retransmit the message. So instead of sending exactly the same message, sent a slightly different message. That meant that there was a slightly different ciphertext than we had the previous time. And both of these messages were intercepted. So that means the Allies now had access to both C and C prime. They didn't know anything about the key. They didn't know anything about the original messages. Well, maybe they knew a little bit about the original messages. And that's what's going to help them, given these two ciphertexts, figure out both the key, and once they have the key, the structure of the Lorenz. So what is the result of XORing these two messages? And that means for each bit, we're going to go through the bits of the messages, XORing each bit. And I want to introduce a new variable here. So the key that the machine generates we'll call K. That's the key that the machine generates starting from configuration C0. So which one of these is the value that the interceptor would get by XORing the two intercepted ciphertexts? So the answer is M XOR M prime. The reason for this is because each ciphertext is the result of XORing a message with the key. So C is equal to M XOR K. C prime is equal to M prime XOR K. Note that the K is the same in both cases. So if we XOR C and C prime, that's going to be M XOR K XOR M prime XOR K. And the really useful thing that happens if you're trying to break this cipher is these two Ks will cancel out. So that's why you end up with M XOR M prime. So that doesn't tell right away what the message is. If the messages were exactly the same, M XOR M prime would just be 0, and this wouldn't tell us anything. The ciphertext XORed will be 0. But they weren't exactly the same. So when the Allies XORed these ciphertexts, they didn't get all zeros. And the reason for that was because of the abbreviations that were used in the transmission. An example would be if the original message has Sprucknummer, meaning serial number, well, maybe in the retransmission, it became an abbreviation Sprucknummer. And that would mean, well, the places where the letters start to be different, we start to see differences between the ciphertext and the ciphertext prime. And unlike the key, which was pretty close to random, there were a lot of things you could guess about the messages. The Allies had a pretty good guess that the message was in German. So the Allies could start trying, let's say, the message, we'll guess it's M star. Then we could try seeing what we get when we do M star XORed with the C, XORed with the C prime. So we can make some guess for the message, try XORing it with the intercepted ciphertext. That should give us back the other message, and we'll look if that looks like a possible message. This is definitely a painstaking process, but something that can be done. Once you get the two messages by this guessing process, then it's easy to find the key. Once you have the two messages through this guessing, you had the ciphertext intercepted. Now you know the key. So learning the messages might be useful. By the time you've done all this work, maybe it's too late for the message to be useful, but learning the key could be really useful. So this was done by Colonel John Tiltman, who took these two intercepts and determined the key that produced them. And they had enough content here that there were 4,000 letters in the intercepts, so they had a 4,000 long key. And this key was given to Bill Tutt. This was his first assignment at Bletchley Park, was to try to make sense of this key. And after about 6 months of work, he was able to determine the machine structure that produced that key. And this is what it is. You have 5 lines going in. This is the 5 bits in the Baudot code for encoding each character. And the rest of the machine is to produce the key bits. And there's an XOR with each of these wheels. So these wheels will rotate with each character. And then there's another set of wheels that sometimes rotate and sometimes don't. And we have these 2 M wheels. Based on the result of XORing the M wheels, either all of the S wheels rotate one position for that character, or none of them do. And this was really the biggest weakness in Lorenz cipher, was that the S wheels all moved at once. So this is the structure of the machine. So the message, each letter would be divided into 5 bits, and those would be XORed with the value coming from the corresponding K wheel. And so these wheels would rotate with each letter. And at each position, they either had a 0 or a 1, depending on whether there was a pin in that position or not. And each wheel had a different size. The last one had 23, the first one had 41. They were different size wheels. And this would also be XORed with the result from the S wheels, which works similarly. They also had positions that were either 0s or 1s around the wheels. The difference was the K wheels turned every character. The S wheels only turned conditionally on the result of 2 other wheels, which were the M wheels. The M1 wheel would turn every time. The M2 wheel would rotate depending on the value of the M1 wheel, and depending on the XOR of those, either all the S wheels would rotate by 1 or none of them would. And then the result of all these XORs is the ciphertext. So this is similar to the idea behind a one-time pad. We're XORing message with key, but the key is not a perfectly random sequence. It's the key generated by this machine. So to break the cipher, once you knew the structure of the machine, that's not enough. You need to know the initial configuration. So here's the intercepted message that was intercepted over the radio. And we can think of all the characters in the message. And the important thing to remember about the Lorenz cipher is that the message encoding, each character is encoded into 5 bits using the bit-O code. And so the ciphertext is in the same sequences, where each ciphertext bit corresponds to one bit of that letter. The next one corresponds to the next bit of that letter. So we can think of the ciphertext being broken into channels corresponding to each part of the letter. So that means each channel would be the sequences that repeat every 5. So this would be part of the first letter, part of the first letter. This would be the second part of the first letter. This would be the second part of the second letter. And this would be the third part of the first letter. This would be the third part of the third letter, and so on. So we can think of each of these as a separate channel. So what we're going to do is use a new notation. We're going to subscript Z by channel and the letter for that channel. So Z C sub I is the ith letter for channel C. So in terms of this mapping, if we look at channel 0, that's going to be Z0, Z5, Z10. So we can just break the ciphertext up into channels. And the key reason for doing this is because of this weakness that was noticed in the cipher. And the key weakness is that all of these S wheels move in turn. So either when we advance one position, they're the same for all the channels, or they advance by 1 for all the channels. So the value of each of these depends on the message. It also depends on the outputs of the K wheels, and it is also XORed with outputs of the S wheels. And by separating it into those 3 pieces, we're going to be able to take advantage of properties that they have. So the key insight is that the S wheels don't always turn. So if you look at subsequent characters, there's a good chance that the S wheels have not changed. So we're going to define delta Z sub Ci as the difference between 2 subsequent characters in the ciphertext for that channel. So that's XORed with Z C of I plus 1. And now because this is for that channel, these are 5 characters apart in the intercepted ciphertext, but they're adjacent for that channel. So what happens when we look at these values for 2 different channels? So we're going to look at channel 0, and we're going to XOR that with the delta value for channel 1. So plugging in the definitions, well, that's just the result of Z XORing all of these values. But where this becomes valuable is because we can break these down into the 3 parts. So let's break them down into parts, separating the M, the K, and the S parts that combined into this ciphertext. And so what we get is these 3 things. So for the message bits, we have the XORs of all the message bits for the 2 channels adjacent, and the key bits XORed with the message bits. And then we have this for the S bits as well. And so I want to ask a brief quiz here. For each of these combinations, we'll call them, this is delta M, delta K, and delta S. So supposing we could separate each of those, the question is which of these inequalities are likely to be true? And so each one we're asking whether the probability of that part being 0 is greater than 1/2. If it was a uniform distribution, well, the probability would be equal to 1/2. If it's not uniformly distributed, then the probability could be less than or greater than 1/2. And I'm asking here, are there any of these that we can be confident, or at least have a good likelihood that the probability of the delta for that component is equal to 0? And let me remind you what the components are. The message is text in the language, and in this case it's in the language German. These are the K wheels. Each wheel rotates with every character, and they have pins around the wheels deciding if it's a 0 or a 1. And these are the S wheels. And the S wheels rotate only when the output of the M wheels is a 1. So sometimes they don't rotate at all, sometimes they all rotate at the same time. So the answer is actually both the first and the third are likely to be significantly greater than 1/2. The second is not. So assuming the keys have as many zeros and ones as the good keyboarder should be designed to have, this is likely to be equal to 1/2. There's no reason to expect it to be greater than 1/2, any more likely than it would be less than 1/2. We're XORing 2 consecutive key bits. The other two are different from 1/2, and this is what gives us the opportunity and what gave Bletchley Park the insight needed to break the cipher. For the third one, this follows from the structure of the machine. When the S wheels advance, well, this probability is about 1/2. But when they don't advance, delta S is always 0. So this means that the probability that delta S is 0 is significantly greater than 1/2. And it turns out, for the structure of the Lorenz machine, it's about 0.73. And to know that, you'd have to look in more detail at the structure of the M wheels and to know how frequently the S wheels advance. And when they don't advance, we know the result is 0. When they do advance, about half the time, the result will be 0. Getting the first one right required a little more linguistic insight. And the reason this is greater than 1/2, well, this depends on subsequent message letters. And if adjacent letters in the message are the same, that ensures that delta M is equal to 0. And it turns out that this is a property that many languages have. You can see that English has it. We have repeated letters here. We also have some repeated letters in wheels. So it's more likely than you would expect by just the normal letter distribution for subsequent letters to be identical. And it turns out that this is a property of German, that about 3.3% of digraphs, meaning pairs, two adjacent letters, are the same letter. That means the probability that the messages are equal, well, they could be equal for lots of other reasons, but this biases it towards being more likely to be 0 than non-zero. And it turns out that that's 0.061 probability for German. Both of these are numbers that you didn't have enough information to guess on your own. You would need to have an analysis of German text to know that this is the probability here. And you would need a lot more details on the M wheels to be able to get that. So don't feel bad if you didn't get this quiz correctly. Although the structure of the machine should have been enough to guess that this was greater than 1/2. And if you are familiar with German or could guess that it has properties similar to English, you might have been able to get this one as well. So now we've got this great property. We've got two things that are significantly different from 1/2. Can we use that to break the cipher? So now the question is, assuming that the probability of delta K is 0 is still 1/2, does knowing that these probabilities for delta M and delta S being greater than 1/2 help us? And remember that our ciphertext values that we're intercepting are the XOR of delta M, delta K, and delta S. So the choices are yes, that it definitely helps us. It doesn't necessarily help us, but if we knew something more about K, maybe it would help us. It doesn't necessarily help us, but if we knew something more about M, maybe it would help us. So the answer is it only helps us if we know something else about K. And the reason for this, well, if K is uniformly distributed and we're XORing with these other values, whatever patterns that M and S have are lost when they get XORed with K. This is the whole point of the one-time pad, that we can XOR a random key with a message and hide all the statistical properties in the message. So this is not the case that it helps us by itself. If this was all we knew, well, this is a potentially interesting property, but we need to know something more in order to use this to help break the cipher. Knowing something more about M would be great. That's the message we're trying to decrypt, but that's separate from being able to use this property in a useful way. So what we really need to do is know something more about K. So what more do we know about K? So here's our Lorenz machine, and we have the K wheels. That's what produces K. And each of these wheels might be a different size. So the first one has 41 positions that are all set to either zeros or ones. The second one has 31. If we're looking at delta Z for two channels, remember what we were producing here was looking at the XOR of delta Z from channel 0 XORed with delta Z from channel 1. So let's focus just on these two channels, the outputs. So the question is, how many different configurations are there for the first two K wheels, the ones for channel 0 and channel 1? And the numbers here are the size of those wheels. The answer is, well, there are 41 different positions for the first wheel, and we multiply that by 31 different positions for the second K wheel. And so that means that every 1,271 letters, those wheels would repeat. And there are only 1,271 different possible settings for the K wheels. And remember, based on the intercepted messages, they learned enough about the structure of the machine to know what the bits are around these wheels. So it's only necessary to figure out the right configuration. So certainly today, being able to try 1,200 some possibilities would be trivial with a modern computer. And you might wonder why, when they encountered this at Bletchley Park, they didn't just go down to the store and buy a computer to solve it. But this was 1941. Computers didn't exist yet. They had to invent one first. And in fact, arguably the first computer was invented to solve exactly this problem. Before we get to that, I want to make sure that we actually have enough of an advantage here that trying these configurations will help. So let's look at the probability that if we guess the right key, we'll be able to tell that we got the right message. So if you recall the separate channels, so we divided the cipher into the message part, the key part, and the part from the S wheels. And now we've concluded that if we can, so we're going to try 1,271 possible settings. So for one of those possible settings, we're going to know all the key bits, and that means if we guess the right setting, the key will go to 0. So now all that's left is the other two parts. So this is what we had before. We knew that the probability of delta M being 0 was greater than half, and it was actually about 0.61 for German because of the likelihood of message letters being repeated. And we knew that the probability of delta S being 0 was about 0.73, and that's because of the structure of the machine, that the S wheels don't advance every step, only when the M wheels are on a 1 do the S wheels advance. And so now we've said if we guess right, that means the probability that the key bits are 0 goes to 1. And it'll be 1 when we guess right. When we don't guess right, it'll be 1/2. So in order to tell if we guess right, well, we need to know that the probability of the ciphertext bits, when we guess right, the probability of the delta z as being 0 will be different from 1/2. So the question is, what is the probability delta z is 0 when we guess right? And remember that what delta z is the XOR of delta m, delta k, and delta s. So to solve this, you need to think about all the different things that would make delta z equal to 0 and compute their probability. The answer is 0.55. So the key is 0. We can cancel that out. So we're left with delta m XOR with delta s. Well, that could be 0 either if delta m is equal to 0 and delta s is equal to 0. Then the XOR of 0 and 0 would be 0. The probability that delta m is 0, well, we know that. That's 0.61. And we're going to multiply that by the probability of delta s is 0, which we know is 0.73. But that's not the only way delta z could be 0. The other way delta z could be 0 is if both of these are 1. So it's the probability they're both 0 plus the probability they're both 1. And these probabilities are 1 minus the probabilities that we have before. So it's 1 minus 0.61 times 1 minus 0.73. And if you calculate all that, you get 0.5506. That's probably a little more precise than it should be, especially because this value is just a guess. We'd have to do a much more detailed analysis of German to know whether that probability is really 0.61, and we'd have to know more about the particular messages that might be encrypted. But this value is pretty far away from 1/2. Any advantage that's that large, if we have a lot of text, we're going to see that pretty clearly. So if we have enough text, we can count the number of positions where delta z is equal to 0. If it's close to half of them, well, then it was a wrong guess. If it's close to 0.55 of them, then we have a good likelihood that that was the right guess. So now all we have to do is feed in the intercepted messages, our guesses for the starting position of the two keys. We need to compute a big summation of these values, of the delta z values with those keys. And If it's close to the length of the message divided by 2, well, that means it was a bad guess. We weren't able to cancel out the key. If it's close to 0.55 times the size of z, well, then it's a good key. It's likely that that's a good guess, and then we should be able to use those key guesses to find out what the actual message was, to decrypt the ciphertext. So this is exactly the problem that what is arguably the first electronic digital computer was built to solve. So with this advantage, there's a good likelihood that you would be able to know when you guess the right key. You need to try all the configurations of K0 and K1. And for each one of those configurations, you have to compute this double delta. What we're computing for each configuration is this double delta, the XOR of 2 deltas. And that involves computing all these XORs. We need the XORs of the keys XORed with the messages and the S wheels. But remember, what we're doing is guessing that this is 0. We don't have any way to predict those S values. We're producing the key values, and we're XORing those key values with the intercepted ciphertext. So we need to do these XORs, XORing out the key, and XORing the key with the value of the ciphertext. So for each character, we're doing 7 XORs, and we're counting the number of times that's equal to 0. So multiplying all those together, we know the total number of XORs we need to do. So we get about 44.5 million. That's the maximum number that we might need to do. If we're lucky, we might guess the right configuration right away, and we could know that that's the right configuration by getting the high number of zeros out. If we're unlucky, we might need all 1271. Normally, we should expect to need about half of that. So maybe on average, we would need about 25 million XORs to find the configuration, the correct value of X, K1, and K0 for one ciphertext. Once we've got K1 and K0, well, we can do similar things to find K2, K3, and K4, and then we can decrypt the whole message. So today, modern processor runs at 2 gigahertz, so you're doing 2 billion operations per second. And one operation could include many XORs, possibly 64 XORs or 32 XORs, depending on your processor. So to do that on a modern processor would take a fraction of a millisecond. To do that in 1941 was a major technical challenge. Computers didn't exist yet, but this was the main impetus for building what was arguably the first electronic programmable digital computer. So the first machine that was built to do this was called the Heath Robinson. It was named after this British cartoonist who drew cartoons of crazy machines to do operations. This one was for peeling potatoes. And the timeline of this is quite interesting. So the first operator mistake, the retransmission with abbreviations, happened in August 1941. That was intercepted. Over the next year, that was enough to learn from the 2 intercepted messages the structure of the machine, then to understand it well enough to develop this technique, the double delta technique, for finding the correct configuration and to break messages. By December 1942, they decided to build a machine and put the resources necessary to design and build a machine. It was requested to be done by June of 1943. It was actually delivered 3 months early. By April 1943, they had the first machine delivered and operational, and it could process messages about 2,000 characters per second. So it was able to do 7 XOR operations in half a millisecond, running this paper tape through at 20 kilometers per hour. This was not quite fast enough. A lot of the value in decrypting messages, especially in wartime, is being able to decrypt them before what the message is describing actually happened. So they built a faster machine. And the faster machine was called Colossus. This was operational by January 1944. And the big change that made Colossus much faster and more useful than the Heath Robinson machines was that they replaced the configurations which were previously on a tape with an electronic key text generator. The logic is doing all the XORs and counting the number that are 0. And then it's printing out those tallies so you can go back and find the right configuration. And the ciphertext is still on a paper tape. This is spinning through about 50 kilometers an hour, which is a pretty impressive sight when it was operating, processing 5,000 characters per second. And what made this arguably the first computer was because of the electronic key text, this logic was a little bit programmable. It didn't do always exactly the same thing. There were ways to program it to do slightly different operations depending on what the analysts thought was the most useful thing to do with that intercepted ciphertext. So this was arguably the first programmable digital electronic computer. It wasn't fully programmable. It wasn't a general purpose computer, but it could be programmed to change its behavior slightly. You can see what this looked like during World War II. There are very few pictures of it. This was a very secretive operation. And the machines were actually all destroyed after the war. A lot of the value in breaking a cipher is to make sure that no one else knows that you've broken it. This is different from academic cryptography, where people like to publicize when they break ciphers. In military cryptography, the whole value of breaking a cipher is that your enemy keeps using it. So you want to keep it very secretive that you've done that. A lot of the work on Colossus was not declassified until the mid-90s. Today, if you visit Bletchley Park, you can see a replica, a rebuilt version of Colossus. This is my picture of it from 2004. It does look very similar to the black and white picture from World War II. Unfortunately, they don't operate it frequently, so you won't get to see the tape spinning through at 50 kilometers an hour and all the crunching going on, unless you're very lucky to go one of the few days a year that they might actually operate. So these Colossus machines had a huge impact on World War II. By the end of the war, there were 10 of them continuously operating at Bletchley Park, decrypting all the traffic that they could intercept. They decoded over 63 million letters of messages in Axis communications. Among the things they learned from them were the troop locations of the Axis on D-Day. This was very helpful for planning the operation. So why did I tell you this story? Well, first of all, it is an important story in the history of both the world as well as computing. But this isn't meant to be a history class, although I certainly like to have historical excursions when I can. But it's also very relevant to modern cryptanalysis. Modern ciphers are much better than the Lorenz cipher. And the main reason for that is we can use computing power to do the encryption. But the basic ideas are actually quite similar. So the goal of the cipher is to hide all the statistical properties that are inherent in the message. And they're present in the key, at least the generated key. The actual key, we hope, is perfectly random. Finding perfect randomness and getting it in computing is quite challenging. But let's assume we have a perfectly random key. What we learned from the perfect cipher analysis is that the key must be shorter than the message. That means in order for the cipher to work, we need to generate more key bits than we actually have. And so even if the original key, and you can think of that in the case of Colossus as the configuration of the machine that comes from some code book that could be perfectly randomly generated and shared between the endpoints, that is only the starting configuration. There's some larger key that has to be generated to produce the ciphertext. And so both the key and the message have some statistical properties. The goal of the cipher is to hide all those properties. The goal of the analyst is to find statistical properties in the ciphertext and then to use those to break the key or the message. In the case of Bletchley Park breaking the Lorenz cipher, they found the statistical properties when you looked across channels at subsequent letters. There were some statistical properties that were not hidden by the cipher. And that was because of a mechanical weakness, that all the S wheels either all moved or didn't move. And that meant that instead of having the long period with no repetition of 19 million letters that the users of the Lorenz machine thought it had, the Allies could break that down and find a pattern that was only 1,271 letters long with much fewer configurations to try to have a good guess if the cipher with many fewer guesses needed. In a modern cipher, we think of that as a mathematical weakness. There's some problem in the mathematics of the cipher that leaves some statistical property that a cryptanalyst could exploit. The other relevance to modern cryptanalysis is it's really lots of hard work to do that. I find it quite amazing what Bletchley Park was able to do with Colossus. It still took 6 months of effort looking at those two messages to figure out the key and interpret the key structure from that. That requires an awful lot of trial and error and a lot of creativity, but also a lot of tedious work. In modern cryptanalysis, we try to do as much of the tedious work as possible by computers, but there's still lots of hard work that goes into breaking a cipher. And motivation certainly helps a lot for that. In the case of Bletchley Park, the fear that your country was under attack is a pretty strong motivation. So we won't talk in much detail about modern symmetric ciphers in this course. There's a couple of reasons for this. One is that I want to get on to uses of ciphers, which I think is more important and more interesting for most people. Very few people today need to implement a cipher. You really should use library implementations of ciphers in any serious application. It's certainly useful to understand more about what's going on beneath the scenes. But even fewer people should be designing new ciphers. You would have to have very unique requirements to think that you're better off designing a new cipher yourself than using a standard, well-accepted, carefully analyzed cipher. So most of the time, we view ciphers as black boxes that are taking in messages and keys and outputting ciphertext, and assuming that they have the properties that we need. Certainly, we've proven that no cipher really does. We've shown that the only way for a cipher to be perfect is if the key space is at least as big as the message space, and that's impractical for any useful use. We can group modern ciphers into two types. There's stream ciphers and block ciphers. And the difference is a stream cipher, we've got a stream of data, and our cipher can encrypt small chunks at a time. You can think of the data streaming through the cipher, encrypting usually at the level of 1 byte at a time, whereas a block cipher, we think of our data in larger chunks, and the cipher encrypts a block at a time, and usually a block size is at least 64 bits, can be longer, up to 128 or 256 bits. These are sort of really the same thing, right? The only difference is changing the block size. If the block size was small enough, it would become a stream cipher. If the block size is large enough, we can think of it as a block cipher. But there's enough differences in the way you build ciphers that different ciphers are designed for each purpose. The most important block cipher today is known as AES, and this stands for the Advanced Encryption Standard. And AES is a block cipher. It works on blocks of 128 bits. AES is the result of a competition that was run by the United States National Institute of Standards and Technology, more commonly known as NIST. And this competition was started in 1997 to find a cipher to replace DES, which was the data encryption standard, which had been a standard for the previous 30 years. That contest ran from 1997. They had a very open process. This is very unlike the process that was used to select DES as the previous recommended cipher. This led to 15 submissions for round one, and some of these were actually completely broken. Others were rejected for other reasons. This was narrowed down to 5 finalists, none of which were seriously broken, and one winner which was selected. The main criteria for selecting the winner of AES were the security of the ciphers. And this is really the hardest thing to measure. We've seen that other than the one-time pad, provable security is not achievable for most ciphers and not achievable for any cipher that was a candidate for AES. The way this was measured was trying to estimate the security. And the main metric for measuring security was looking at the actual number of rounds in the cipher and dividing it by the minimum number of rounds that were breakable in some sense. And breakable here is very much the academic definition of breakable. You didn't need to be able to extract a message or a key. Anything that showed you could reduce the search space even a little bit would be enough to show that it was breakable for that number of rounds. The other properties were easier to compare and measure, which were speed, implementing it both in hardware and in software, and simplicity. And simplicity is usually against security, right? To have higher security, we want more confusion. We want to do more transformations to the data. That goes against simplicity. Simplicity aids the analysis to make it more clear whether the cipher is secure or not. So the winner of the AES competition was a cipher known as Ryandahl, which was developed by 2 Belgian cryptographers. The good thing about it winning AES is now we don't have to figure out how to pronounce it correctly in Belgian. It's now called AES. The best known current break against AES is very theoretical. So with 128-bit keys, that would mean a brute force attack that tries every possible key would require, on average, 2 to the 127 attempts. You're expected within half the 128-bit keys. So you've got 2 to the 128 total keys. you expect to find a break after testing half of them. So the expected cost of brute force attack is 2 to the 127. The best known attack removes less than 1 bit of security. So that's the best known today. And 126 bits of security is well beyond what's practical to imagine implementing, even with a huge amount of computing resources. So we're not going to get into the details of how AES works, but I want to talk a little bit about the main components of it. So there are two main things that go into AES and go into almost all modern block ciphers. They all involve XORs. So we saw that in the one-time pad. And they're XORing some round key, which is generated by a key schedule, some process of generating new keys for each round. And then what's going into that, there are two main operations. One is shifts, so permuting bits, and there would be a map that would move bits around. This is better than just doing only XORs because we're moving data around instead of just XORing and changing it. The other thing that's really important for a cipher to be hard to cryptanalyze is to have some nonlinearity, something that is very difficult to analyze and mixes up data in a way that is nonlinear. This is done basically by having lookup tables. So what's called an S box is something that takes in 8 bits. In this case, it could have different numbers going in, and basically has a lookup table. So that's going to have 256 entries, mapping each set of 8 bits to some other set of 8 bits. And designing that lookup table is a challenge. We want the lookups to be as nonlinear as possible and make sure there are no patterns in the data in this table. And so the way AES works is combining shifts and S boxes with XOR to scramble up the data, and it's going through multiple rounds. So we'll take the outputs of this, put them back through a series of shifts and S boxes again, and keep doing that. And the number of rounds depends on the key size. So for the smallest key, for the 128-bit key, which is the smallest key size for AES, we would do 10 rounds going through this cycle, getting the output ciphertext for that block. So the details are definitely more complicated than this, and getting them right is very hard. There's lots of great resources that explain AES in detail, though. For our purposes, we're going to think of it as a black box that we can use encryption in our protocols. We're going to assume it has the properties that we want it to have and not need to look in more detail at how to actually implement that in a modern cipher. So we've reached the end of Unit 1. Let me remind you what we've covered. So we covered symmetric crypto systems and introduced the terminology and definitions we need to talk about encryption. In particular, we know what it means for a crypto system to be correct, that encryption and decryption are indeed inverses. And defining security is a much trickier thing, and we talked about ways we could define security for a symmetric crypto system. We introduced the one-time pad, which is a very simple but important crypto system, and it's all based on using the XOR operation. And as long as we have a perfectly random key that's as long as the message, the one-time pad gives us perfect security. And we looked at a formal way to define what a perfect cipher means and prove that the one-time pad has that property. We also saw that in order to be perfect, a cipher has to be impractical, that the number of keys has to exceed the number of messages. And that means that every cipher that's used in practice is potentially breakable. We saw one very interesting example of that with how the allies at Bletchley Park were able to break the Lorenz cipher. And we talked about modern symmetric ciphers, which take advantage of computing power, following many of the same principles of the historical mechanical ciphers like Lorenz, but using modern computing power and new ideas about how to scramble data to produce much more confusion and make things much more challenging for cryptanalysis, even when attackers have access to the huge amounts of computing power available today.
I hope you enjoyed Unit 1 and have a good understanding of some of the theory behind symmetric ciphers and how they're constructed. In Unit 2, we'll look at how to actually use symmetric ciphers to solve problems like sending a message securely between two parties over an insecure channel like the internet, and being able to use symmetric ciphers to play games online and to do important things like managing passwords. Hope to see everyone back for Unit 2.
So welcome to Homework 1. The way homeworks will work in this class is a little different from what you might expect if you took CS101 with me. So there'll be regular homework questions. These will mostly be multiple choice or questions where you need to enter a number or a string. They might involve using programming to solve problems, but you won't be expected to submit code. You'll be writing programs to be able to answer the questions that are provided in the homeworks. There'll also be open discussion problems, and these will usually involve either designing a solution to a problem, designing a protocol, perhaps, or analyzing a provided solution. There's no graded aspect to these discussions, but I think it'll be a valuable part of the course for you to think on your own how to solve these problems, and then to join the discussions in the forums to see how other people have solved them and to see whether your solution is popular or other people notice problems in it. The third kind of problem will be challenge problems. These will be problems that you can submit answers to. They'll be separate from the regular homework, and these are problems that we expect to be quite challenging. They'll probably require a fair bit of time to solve, and they'll get more challenging as the course goes on. It's not necessary to solve these to feel like you're following the course and getting a lot out of the course, but if you do have time and enjoy challenges, I hope you'll tackle the challenge problems as well. If you are able to solve a challenge problem, please don't spoil the fun for other students in the class. Don't post your solution to the problem until after the deadline has passed. The first 3 questions on this homework see that you understand conditional probability. So for these 3 questions, we're going to use the relative frequencies of vowels in English, and I'm giving you those results as a percentage of all the letters in a sample of typical English text. So you can assume that 13% of all letters in the text are the letter E, 8% are A, 7% are O, 7% are I, and 3% are U. Obviously, this is not a very audacious sample of English text. So for question 1, assume some letter X is drawn randomly from English text with the same distribution as we've collected here. Give the value of the probability that X is a vowel. Your answer should be in the range from 0 to 1. So a real number where 0 means it could never occur, 1 means it always occurs. The answer is 0.38, and that's just the sum of the probability for each vowel. Summing those up, we get 0.38 as the probability that a randomly drawn letter is a vowel. For question 2, give the conditional probability that X is an E given that X is a vowel. The answer is 0.34. So to compute this, we need to use the conditional probability rule. We already know the probability that event B, which is X is a vowel, we computed that in question 1 as 0.38. What we need is the probability of A intersect B. Well, B is the events where X is a vowel. A are the events where X is equal to E. Whenever X is equal to E, it's also a vowel. So that intersection probability is the same as the probability that X is equal to E, which is 0.13. And dividing those, we get the result 0.34. So for question 3, compute the probability that X is a vowel conditioned on X is not the letter A. The answer is 0.32. And we're computing this using the conditional probability rule. So that means we need the probability of A intersect B divided by the probability of B. In this case, B is the case where X is not A. So that's 1 minus the probability where X is A, which is equal to 0.92, since the probability that X is A is 8%. The intersection probability is the probability that X is a vowel intersected with the probability that X is not A. So that's the probability for all the vowels other than A, which is adding 0.13 plus 0.07 plus 0.07 plus 0.03, and there we get 0.30. And when we do the division, we get 0.32. And this makes sense. Previously, we computed the probability that X is a vowel by itself was 0.38. If we know X is not A, we expect that probability to go down, which is why we get the lower value, 0.32 here. The next question checks that you understand one-time pads. So Alice and Bob have agreed on a perfectly random key, and that Alice will send Bob the answer to the question, are you taking CS387, as either the single character Y or the single character N. This will be encoded using the string to bits procedure, which takes in a string and gives you a list of bits. And the result of string to bits Y is 1011001, and the result for N is 1001110. Mallory knows nothing about the key or the message, but she intercepts the transmission between Alice and Bob and intercepts this sequence of bits. And Mallory wants to cause trouble between Alice and Bob, so she wants to make Bob hear the opposite of what Alice said. So if Alice sent a Y, Mallory wants Bob to hear an N. If Alice sent an N, Mallory wants Bob to hear a Y. So what should Mallory send instead of the original message that she intercepted? And your answer should be in the form of 7 bits, each of which is a 0 or 1. So once you understand the answer to this, I want to encourage you to join an open discussion question, which is there a way to solve this problem? Without using anything other than a one-time pad, is there a way for Alice and Bob to communicate correctly the answer to this question and know that it can't be altered in transmission and still preserve all the privacy properties of a one-time pad? So the answer is 10110001. And the way to get that is to look at the 2 possible messages. So we had for Y 10110001. For N, we had 10011110. And we want to do is XOR them to figure out the difference between those 2. So the XOR of Y and N is equal to 00101111. And so this is the value that will flip a Y answer into an N answer. Now we want to XOR that with the actual message that was sent. We don't know the key, but we know that that message is the result of XORing Alice's message with the key. And so by XORing those, we get this value, 10110001. And if that's what Mallory sends, when Bob XORs that with the key, what Bob will get is the XOR of Alice's message. Alice's message XORed with this value, which will flip Alice's message to be the opposite. The point of this question is to illustrate the malleability of the one-time pad. Someone who intercepts the transmission can alter it and change the meaning in predictable ways. This is a very dangerous property for a cipher to have. So a popular toy cipher is a monoalphabetic substitution cipher, where each letter in the alphabet is mapped to some substitution letter. This could be the same letter, could be any other letter in the alphabet. And decryption is done by the reverse mapping. So we provided Python code to make this more specific, what a monoalphabetic substitution cipher does. One way to prove that a monoalphabetic substitution cipher is imperfect is to use Shannon's key space theorem, which says that the number of keys in a perfect cipher must exceed the number of messages, or be equal to it. Assuming a 26-letter alphabet, what length message do we need to show that the key space for the monoalphabetic cipher is too small to be a perfect cipher? For your answer, give a number, which is the minimum length message needed for this proof. So the answer is 19. To solve this, we need to compute the key space. Well, the key is just a permutation of the alphabet. We have 26 choices for what A could map to. We have 25 choices for what B could map to. We have 24 choices for what C could map to, and so on through the alphabet. This is equal to 26 factorial, which I won't attempt to write out, but we'll show you in Python. So let's define a factorial function, and we get this rather large number. What we need to know now is how this compares to the message space. The number of possible messages of length n, well, each letter in the message can be any letter in the alphabet. So that's just 26 to the n. So we're going to find the first number n, where 26 to the n exceeds factorial 26. And we get 19. And we can confirm that 26 to the n is indeed greater than factorial of 26. 26 to the 18 is less than it. For this question, your goal is to provide a shorter proof that the monoalphabetic substitution cipher is imperfect by showing some 2-letter ciphertext that could not possibly decrypt to the string CS for any key. There are many answers to this. Any 2 letters that are the same cannot decrypt to CS because the way the monoalphabetic cipher works, every time we see a G, it maps to the same letter. So G could decrypt to C, but that would mean the other G also decrypts to C, and we can't get CS out. So one useful property of XOR is that we can use it to share a secret. And that means we can take a secret, divide it among a group of people, where each person in that group does not gain any information about the secret, but by combining their shares, they can determine the secret. So here's an example. So Alice has some secret X, and she wants to keep a backup copy of X. So what she does is first she generates some key, selected randomly and uniformly from the key space. Then she computes S, which is K XORed with X. So that means S of I is equal to Ki XORed with Xi. Then she gives K to Bob and S to Colleen. This means by combining K and S, Bob and Colleen can produce the secret X. Either one by themselves has no information. K just has a sequence of random bits, and Colleen just has X XORed with a sequence of random bits, which provides no information about X. So this works fine as long as Alice trusts Bob and Colleen not to collude and to give back the values of K and S when she asks for them. But what if she's worried that they might collude? So she decides to share the secret among more people. How many key bits will Alice need to share a 100-bit long secret among 4 people? The answer is 300. What she'll need to do to share the key among 4 people, Alice will need to compute 3 keys of 100 bits long. And one way to do this is to give one person the secret XORed with all of the keys, and to give each person one of the keys. There's no way to do this with perfect secrecy using fewer than 300 key bits, because that would mean either we're not fully sharing the secret, that some party has no part of some part of the secret, or that we're reusing key bits. The question for the challenge is you're given 2 intercepted ciphertexts, C1 and C2. You can see those both below. And you know that they were both encrypted using a one-time pad using the same key. They're also both messages in standard English. Your goal is to figure out what the 2 plaintext messages were. You can enter these in any order, and it should be clear to you that which one is which can't really be determined. But figure out what the 2 plaintext messages corresponding to the 2 intercepted ciphertexts are. And I should mention that you can assume that both messages are in English and were encoded using string to bits that maps English to sequences of bits. I'm not going to provide an answer to this one, but I'll give you a hint how to get started if you were stuck. And that would be to try common English sequences of letters. THE would be a good one to try, and assume that probably appears somewhere in at least one of the quotes. And you can try THE at each of the starting positions, and then assume that's in, say, message 1. So you're going to guess ciphertext 1 is THE encrypted with a key. Then you can compute the key from this. That gives you what the likely key is, XORing string to bits of THE with the corresponding part of that ciphertext. And then you can XORing out the guessed key from the corresponding part of message 2. If that looks like something that might be part of an English message, well, then that's a good guess, and you can work on from there and start expanding the letters that you've guessed to see ones that produce reasonable results for both ciphertexts. This is a fairly manual process. If you wanted to do this more automated way, well, then you'd use properties of English to automate this kind of guessing and expansion for you.
Be on the forums and some interesting questions to answer. So let's get started looking at some of those questions.
Yeah. Our first question comes from Ensa, who wants to know how many of the questions on the future problem set in the final exam will be primarily programming-based questions and how many will be primarily mathematics-based.
So it's going to be a mix. Cryptography is really a branch of mathematics, so there's a lot of math in crypto, but we also want to build things and we are interested in programs and the computing aspects of that. So there will be questions that either require you to write a program, or more often questions where to solve them well, you probably have to write a program, but the goal is to solve the question, not to write the program for its own sake. So there will be a mix. There'll be a few questions on each homework that do involve writing programs, many that don't though, and those will be more involving the mathematics.
So in lecture, you mentioned that the one-time pad is the only perfect cipher. Time Zombie writes wanting to know why this is true.
So I probably overstated things a little bit saying this is the only perfect cipher, that you could certainly construct ciphers that are perfect and are not exactly the same as the one-time pad as we've described it, but they'd be essentially the same. And what Claude Shannon proved is that to be a perfect cipher, you have to have the key space as large as the message space, and you can never reuse a key. So every bit of the message corresponds to a bit of the key. And then with the one-time pad, we're XORing that. We could do some other operations that would be equivalent of XOR and have another cipher that would be perfect. But the important thing that was proven is that if the key is smaller than the message, there's no way for the cipher to be perfect. There must be some information leaking to an attacker that potentially could be used to break it.
Okay. And then as a follow-up to that, he also wanted you to comment on quantum cryptography.
Cool. Okay, so quantum cryptography is a very interesting topic. And there's really 2 sides to that people think about. The first is quantum key distribution, which is to take advantage of properties of quantum physics to be able to send a message where even if someone intercepts it, they cannot replay it. And that means that the 2 parties at the end can know that if they establish a key, if that message got through between them and they can verify that they received the right message, that there was no physical way it could be eavesdropped on. Because the properties of quantum physics are that if you observe properties about a photon, you can observe some parts of it, but you can't observe the whole thing. You can observe, say, both the momentum and the spin at the same time. And I'm not an expert in quantum physics, so that may not be exactly right. But you can observe, and this is Heisenberg's uncertainty principle, you can observe every property of the photon at the same time. So you can set things up. And I won't go into the details of that now. We may talk about that in one of the, maybe Unit 7. I think that would be a good topic to bring up again and go into a little more detail. The other interest is in quantum computing, which potentially offers a way to solve problems that we can't solve with classical computers in an efficient way. And the most interesting question there is factoring, which in Unit 4 we'll talk about the importance of factoring being hard for breaking RSA, for the security of RSA, relying on it being hard to factor numbers that are multiples of 2 large primes. There are ways, if you have a quantum computer, to do factoring efficiently in a polynomial number of steps, which no one knows a way to do with a classical computer. So if it was possible to build a large quantum computer, which no one has been able to do yet, but in theory could be done, then you could break cryptosystems like RSA that depend on factoring being hard, because you could factor large numbers using your quantum computer. So both of those are sort of interesting aspects where the sort of deep properties of quantum physics can be used either to the advantage of making something more secure or to the advantage of the attacker. And we'll talk about the impact of quantum computing on factoring a little bit in Unit 4.
Okay, cool. I look forward to it. Thank you. Now I'd like to talk about the open discussion question posted in Homework 1. To review, Alice wants to send a message to Bob using a one-time pad to let Bob know yes or no if she's going to be taking CS387. And they're worried about Mallory, who could possibly intercept the message and then change around the message so that Bob would get the wrong message.
And we saw in the question that Mallory could, whatever she intercepts, she can't tell whether it's yes or no, but she can XOR it with the difference between yes and no. And that will flip the answer. And some of the suggested solutions were to change yes and no to other things, thinking there was something special about yes and no that those could be flipped. But you can flip anything, and you're flipping it by XORing it with the difference. Whatever was there was either yes or no XORed with some key. You don't know the key, but XORing that with the difference of them will cancel out the y's, or if this was an n, it would cancel out the n's and leave the y. So whatever message was, it can be XORed with a difference. There's nothing special about y or n. It would work, let's say, if you replaced it with yes and not. The difference is just Mallory would XOR it with the XOR of yes and not. So all the solutions that were ideas about changing the content don't really solve anything. Mallory knows the two options, can XOR them, and can flip the content. There were some other approaches that had better success, though.
There was two main styles. For example, Steve Krenzel from Seattle suggested using kind of more advanced crypto tools. He wanted to append a nonce to the message and then hash the entire message.
Okay. So I think what he was suggesting, which is a good solution to this, is to take the yes or no, so you're still giving the response. You're going to concatenate that with a nonce, which is just some random value. We'll call it R. This is a long random value. And then concatenate that with a hash of the y, whatever the answer was, with the nonce. And we haven't talked about hash functions yet in Unit 1, but we do talk about them in Unit 2. And a hash function is just a function that takes some input and maps it in a complex and unpredictable way to some other value. And that's useful because Bob can't predict what this value is without knowing what the value of R is. And if the value of R is random and not known to Bob, there's no way for Bob to predict the output of this hash. If he tries to change this, well, there's no way to change it in a way that knows the difference between what the result would be if this was an n and when it was a y. So Bob could flip these bits, but then the hash value wouldn't be correct. And Mallory could flip these bits, then the hash value wouldn't be correct, and Bob would know that it was wrong. So this is a reasonable way to do it. The difficulty with the solution is, well, it involves cryptographic tools that are much more complex than just XOR. Hash functions are things we'll talk about in the next unit, but involve a fair amount of computation. It's not something you can easily do by hand. What we want is some solution that would allow Alice and Bob to do this without using any more advanced cryptographic tools.
Yeah, I guess the other style of solutions was one proposed by Sturcat, which involves sending a number of dashes, maybe 8 or 16 just dashes in a row, and then randomly picking one character to set to Y or N. And then what are your thoughts on that?
Okay, so this is a really interesting idea. So we're going to take, instead of sending just one character, we've got a string of 8 dashes, and we're randomly going to pick one of those and replace it with either the Y or the N. That's going to be the answer. And now this means when Mallory intercepts it, if she doesn't know which one was randomly picked, well, she can XOR out the difference between a Y or N from any one of these 8. But if she picks the wrong one, she's going to change a dash into something else. And I don't know what it would be. We'd have to look at the numbers, but it's not going to be a dash anymore. And so when Bob looks at the result, it's going to look wrong. Bob will know the message was tampered with. It's only if Mallory was lucky enough to guess the right one to flip that she could change the answer. And her probability of guessing it correctly is 1 over the number of positions here. So if we have 8, she has a 1 in 8 chance of guessing the right one and flipping that one. The other times when she doesn't guess correctly, she'll get caught. So this is pretty good. This has a nice property. It means if we make a message long enough, we can make Mallory's success probability as low as we want. But we need a really long message. If we want her success to be less than 1 in 256, we need a string that's 256 bytes long, which not a big deal, but is less elegant. We could get a similar property with a shorter message, is if instead of having only one of them depend on the choice, we make a short message where each of the characters in the message depends on the yes or no value. But Alice randomly picks either to send a Y or a 1 if the answer is yes, or to send an N or a 0. So let's say those are the 4 choices. So she's going to randomly pick. If the answer is Y, she's going to send something like YY, 1Y. Randomly picking for each position whether to send a Y or a 1. When Mallory intercepts this, the XOR between Y and N is different from the XOR between 1 and 0. Those two are not equal. So for Mallory to flip an answer, she's got to guess whether it was a Y or an N or a 1 or a 0. And she can guess and flip one. If she guesses them all correctly, well, then she could flip them all, and Bob would see the wrong answer. But if she guesses one wrong, then Bob will see one of the characters in the string doesn't match. And so now Mallory's probability of guessing them all correct is 1/2 to the power of how many there are. So if there were 4 characters, it would be 1/2 to the 4th or 1/16. But this is a much lower success probability than we had having the string of dashes where Mallory only had to guess one position correctly out of that whole length. Now she's got to guess each position correctly with 1/2 chance for each time. So this just involves Alice picking randomly. So we did need to add something beyond the one-time pad. Alice has to be able to flip a coin or some other source of randomness to decide whether to send the Y or the 1 for each of these 4 positions, or more positions if she wants the success probability to be lower than 1/2 to the 4.
Could you also do like a lowercase y and like a t for true and a lowercase t?
You could, yeah. So probably what you'd have to be careful about if you did a lowercase y and a lowercase n.
It's the difference.
The XOR of those might be the same as the difference between the uppercase y and the uppercase n. I would guess if you did true and false, those would be different, but you should be careful and know that the XOR is not the same. But as long as the XOR is different, then each byte Mallory has just 1/2 chance of making it changed in the right way.
Okay. Yeah, I think that's all we have.
Cool. So thanks for joining Office Hours, and thanks for all the discussion. It looked like we got a lot of good responses to the open discussion questions, so hopefully we'll see that again in homework 2.
Thank you.
Okay, thanks.